saying that we are going to start with this particular script here, which is very, very simple. It's basically the way that we can simulate rigid bodies, which will be the first topic of this course, using some elastic behavior. Okay. In the end, all the materials are elastic in their own way. Okay. So if you take, for example, wood is elastic. Any metal is elastic as well. The problem is how much deformation you can produce applying a standard amount of force. Okay, so but everything is elastic in the real life. You just have to reach its elastic phase in order to see some deformation. Okay, so basically, what's the meaning of this component here, of this function, this script that I have created? This is a cluster, by the way, so you can see that if you hover with the mouse, you will see that there is this kind of blurry preview. It's very stupid. What's the content of this component? It's very stupid because the only thing that it does is basically prepare these values for some mathematical operation. Okay, so as long as you know that the equation for determining the strength is basically elastic module multiplied by the area, and everything is divided by the length of the element. This is what's inside this component here. Okay, that's it. So basically, the only thing that you must respect here are these considerations here. The elastic modulus must be expressed in gigapascal. The area must be expressed in square meters, and the lines that you plug here must be drawn in meters. Okay, so I do recommend that when you work with Kangaroo and you want to simulate some realistic material and deformation, then you must work with meters here, meters. So I will switch unit, for example, in any case, I will switch units in Rhino. So I will be ready to work with meters, and I don't need to reach down to 1 millimeters tolerance, so I will take just 1 centimeter. Okay, so that's my common, usual, standard setup when I work with Kangaroo for realistic simulation. If you don't need to work with real life materials or realistic simulation, then this is absolutely irrelevant. Okay, so just as a previous setup, I do recommend that you switch to meters and you consider at least 1 centimeter as tolerance. And then what this component does is it can use elastic modulus. Now, elastic modulus is specific for any material. So I have just 2 values here in order to understand what's the common range of these materials, elastic modulus. So the lowest value for the elastic modulus belongs to rubber. And of course, because it is very elastic, as you can imagine. So the lowest the elastic modulus, the more deformable the material is. Okay? And the rubber has an elastic module that ranges between 0.01 and 0.1. Okay? It depends on the consistency of the rubber. Now, you might think that this is a very low elastic modulus, but consider that this is expressed in gigapascal. Okay? So this is already prepared for being connected to this input. And so if you consider this, which is 0.1, basically, you have to multiply this by 1 billion in order to know how many Pascal, which is the unit for pressure and other physical properties. So this is being converted into Pascal inside this cluster. So basically, even if this looks very, very small, in the end, it will produce a high value for the strength. Okay, and then there is the area. The area must be expressed in square meters. So basically, if we are working with meters as units, let's say we want to simulate some kind of beam. Okay, we will talk about beams later on, because it is probably the more complex things that you can simulate in Kangaroo, according to my experience, at least. So you will see it is this blank, this white thing here at the bottom, okay? But in this case, we are going to simulate them using the elastic forces, okay? So let's do a very simple exercise. I'm going to take all of these and move it like here. Okay, so I'm going to simulate some kind of beam using elastic properties, elastic forces. Okay, so remember that we are working with meters. So when I start drawing my beam, which is this one, I'm going to set one line, and I'm going to draw a beam which measures something like, I don't know, 7 meters. Okay, like this. I'm going to get rid of the grid as well, so we only see the geometry. Okay. Now we know that if we want to convert this thing here, which is a one segment curve, okay, if we want to convert it into some kind of elastic body here in Kangaroo, we must basically shatter this line here, divide it into segments by using the shatter command, and using the parameters by which we want to split this line. Okay, so parameters, we can use a range, which generates basically a series of numbers between 0 and 1, and we decide how many values is going to be output by this range by defining the number of steps. One consideration here, which is very important, when you work with range, you have to define if the object that you want to shatter, for example, in this case, is open or closed. Because when you have a segment, for example, like this, which is open, okay, so it has start point and end point. And you are deciding basically with steps into how many segments you want to divide this line. Okay, so if I want to divide this line into two segments will be this one and this one. So the range will output this value, and this value. So if I define 2 steps, I will get 3 values here. This is not happening if the curve that I am splitting is closed. So if I, for example, try to split a circle, and I want to split it into 2 segments will be from here to here. This will be the first segment. And from here to here, we already have the division points. And so the range will output only 0. Well, actually, the range will still output the 0, 0, 5, and 1. But the segments here will only be basically these 2 here. We will just have 0.5 here, and 1 will be coincident with 0. This is something that we must take into account if we want to avoid the duplicated points. Okay, so just remember that there are differences if you are splitting an open line or a closed curve. Okay, just a preliminary consideration. So by this, what I'm saying is that I am splitting this curve here into 10 segments. Okay, but if you take a look at range, it is outputting 11 values. Okay, so just for later consideration, if we are going to deal with the range later on, so just remember this consideration in order to better understand what's happening after. So this, in order to work, when you read parameters here, I do recommend that you always reparameterize the line or the curve in general. So reparameterizing is that operation that tells Grasshopper, I don't care about the geometry you are using and what's the geometrical dimension of this geometry. I just want this line to be considered to measure like from 0 to 1. This means reparameterize. So if we reparameterize the line and we use parameters between 0 and 1, all these values will be, let's say, arranged along the path of the curve. If you don't reparameterize the curve, it might happen that all the values between 0 and 1 will only occupy a very small portion, initial portion of your curve. Because if you don't reparameterize, and this curve measures from 0 to 10, for example, and you provide parameters between 0 and 1, you will only be splitting the first part of the line. And then you will have one huge segment here at the end. So I do recommend that when you work with shader, you always reparameterize and then use this 0 to 1 range of numbers. So now here we will see that we have 10 line-like curve, and this 10 line-like curve we can let's say convert them into springs. So we go into goals line, we take length line. This is just a quick resume also on how elastic forces work. So length line basically is asking for the original length. I was just discussing this with a lady from India, I guess, this morning, because she was using, for example, a length factor for the rest length of these lines. Now, normally, when you want to create some kind of realistic simulation, you don't want to provide a different rest length or rest length for the springs. This would be like saying I have a bar made up of steel, and this bar is basically laying on the floor, and by itself it wants to contract or expand. No object wants to contract or expand if you leave it alone. Okay, so this means that the length, in our case, in this particular situation, doesn't need to be fed with any value. Okay, because it says if you don't provide any value, I will assume that the actual length for these segments is the rest length. It means that this body here doesn't want to contract or expand. Okay, so just leave it like this, and we want to deal with strength. And now is when we use this formula here. So what I'm going to do, I'm going to simulate that this beam here is made up of a specific material. And for now, I'm going to use rubber. Okay, so let's say that I use rubber. I just plug the elastic modulus in the number input. Well, I can also skip it, of course, but let's keep it organized like this. Now I need the area, and I will leave this other elastic modulus here in order for use it later. Okay, just to simulate a structural steel. So what I'm going to do now, I need to define the area in square meters. So I will take, for example, a slider between, I don't know, 0. Well, yeah, okay, 0.2, which is 20 centimeters. Let's consider some kind of structural beam, okay, for a building. So between 0.20 and let's say this is a beam which measures 7 meters, so it's already quite a long beam. So I will consider eventually something like 1 meter top. Okay, this will be our B, which will be the base of the beam. Okay, and then I need the height, which will be something between 0. I don't know, 40 up to, if we have 1 meters, let's give it 1.50 top. Okay, and this will be the height of our beam. Now that we have these, we need to provide the area, and this is correct because we are expressing this in meters. So it's 0 meters and 20 centimeters. Okay, so I will create here, for example, well, I could create an expression, but I will use a multiplication, of course. So I just multiply the base by the height, and this is the area. So as you can see, the area is normally, when you work with meters, it's normally a very small value. Okay, so this is a 20 by 40 cross-section beam, rectangular cross-section, and we are getting an area which is lower than 0.1. Okay, but anyway, this is the value for area. Okay, and then we have the line that we want to convert into springs. Now, in order to calculate the strength, I need one strength for each one of the lines that we have here. Okay, so I am not connecting the original line. I will connect the segments that come from the splitting of the original line, because each of them has its own elastic modulus, area, and length. So I will plug this. And this will give us a strength which is valid for any of these segments. And if you take a look at this value here, if you take a look at this, you will see that this is something which is 1. Let's say 14 multiplied by 10 at the 7th, which means that you have to basically move this point here 7 positions to the right. It means that you have basically 4 positions here plus 3. So you have 3 zeros here at the bottom. So it's basically 11,429,000. This is the strength of our springs. Okay. Now, if you consider this, and you consider that eventually, before plugging any value in strength, you have this. Okay. we have another late participant here. So if you consider this, and you consider that the length line normally has a value of 10, and you are about to plug something which has a value of 11 millions, you understand that the strength in a real-life simulation is a very high value. Why it is so high? Because the elastic modulus is expressed in gigapascal, must be multiplied by 1 billion. You multiply this value by a, which is a small number, as we saw, is 0.08, but this is basically eliminating a couple of zeros. So you still have tens of millions coming out from this multiplication here. And then you divide it by the length. And the length is also quite a small value, because normally we are dealing with, this is very common, we are dealing with something like 1 meter, more or less. So basically, the most important thing is this multiplication here, okay? So you see that it provides very, very high values for the strength. Now, if we move on with this simulation, I'm just, this was the important thing. What I'm going to do, I'm just define some anchor point by calculating the endpoints of this line here and plug them both into the anchor point. And I will also turn everything off. I don't want to see anything. And I will apply eventually a load, which is another consideration that my contact in the morning was basically making a mistake. So I'm going to use an evaluate, not this one, evaluate curve. Always when you see parameter, just reparameterize the line and then use the same range. So you will have one division point corresponding to the end of each segment, basically. And I want to use these points here to apply a vertical load. Now, if we work with a real life strength, we must also work with a real life force vector for the load. Okay, so it has no meaning, it has no sense to consider, for example, a vertical force of 0.01. Okay, because here we have a spring or springs that have 1.14 by 10 at the 7th as a strength. So these springs here will not even realize that there is a load applied to the vertices. Okay, so I will take a z vector, apply a negative vertical load, and use a value like which is comparable with the others. So let's say that we have 11 millions in the strength. I will start to define a value starting from, let's say, 1,000. But these are real forces. Okay, so this is something that if you are into construction industry, then you might know that these loads here expressed in newtons have very high values. Okay. The problem with this simulation, and we are going to see it right now, in this moment, in this exact moment, is not the load, is not the strength of the springs, is the anchor points. Because the anchor points normally have a strength of 10,000. But we are applying, for example, now a load of 60,000, which is 6 times stronger than the anchor point. So these anchor points will not be capable of staying in place during the simulation, okay? And please, if you can turn off the microphone, if you have it on in this moment, because I hear echoes and sounds. And so the problem is this strength here. Now, normally, this strength should be the higher value if we want the anchor point to remain fixed, okay? So we are dealing with this kind of value here, which is very, very high. So if we don't provide a value for the strength of the anchor point, which is at least equal to this, these anchor points will move. We will see it during the simulation right now. I'm going to plug the solver, and then I'm going to take the usual Boolean toggle and the button for resetting the simulation. And anchor points over there, springs are here, and loads are here. So now the problem with this simulation is that when Kangaroo works with these high values for strengths, the simulation becomes very, very heavy in terms of calculation and rendering. So you will see that if I fire the simulation, the only thing that happens is that the anchor points cannot bear with this load that we are applying. Okay, so you see that these are the anchor points. They moved down from here to here. Now, in order to avoid this, I'm going to take, for example, the, let's say, a value like 1, 0, and then 1, 2, 3, 1, 2, 3. So 10 millions, which is more or less the value that we have for the elastic strength. So you see that now things are starting to work quite good. And this is what happens if we have a beam made up of rubber. Okay, so rubber is very elastic, and if we work with this kind of loads, well, eventually, and we have a section, a cross section of 20 by 40, it is elastic enough to bend like this. What happens if I switch from rubber to structural steel, which is basically 2,000 times stronger than this one? Oh, of course, we are working with the hardest rubber, but if we lower this value, you would see that the deformation becomes even more evident, okay? But if we switch to structural steel, you see that things start to work like very, very, very slow. This thing is moving up, and it will keep on moving up until it reaches its equilibrium, which is pretty flat in the end, but it's extremely, extremely slow. So you can see that this is rising up, and it's very, very low. So the real problem with this kind of real simulation with like approximating a rigid, an extremely rigid body with elastic forces, the only problem that you have, the real problem that you have, is the speed of the simulation, okay? Just let me mute Tiziano, because I was hearing all the sounds. Okay, so the problem is because of these huge forces that we're using, the simulation becomes very, very slow. So that's why there is a whole section that is called 6 degree of freedom that allows to work with rigid bodies here, okay? So we will discuss these today in order to avoid this kind of problem with the elastic simulation. I'm going to leave it this example here, so you will be able to play with it when we, let's say, end this this course. I will leave it here on top. So you have the script available here and the elastic simulation according to the script here on the right. Okay, so I will leave it like here with one single group. So remember that in case you want to play around with extremely rigid springs, then you can work with this simulation here. I do not recommend it. Okay, you can use it for like preliminary visualization, but as I was saying during the webinar, there is no specific need when you work with elastic forces. There is no specific need of dealing with real forces, real elastic forces, because the deformation that you get in a standard Kangaroo simulation is proportional to the real life scenario. Okay, so if you have, for example, a catenary curve that is anchored here and here, and it stretches down like here, you know that if you scale it, like scale it one dimension in this direction here, you can simply scale the system down to a more realistic deformation, okay? So it's just proportional to the real situation, okay? We will be dealing once again with elastic forces when we will discuss the tensegrity structures, okay, which would be the second step. Okay, so let's go to rigid bodies. So rigid bodies are basically something that in Kangaroo you might want to simulate by using two different sets of things. Well, basically, there are two groups of commands, which are, of course, the Gold's 6 degree of freedom, which is used to define the rigid bodies. And then there is also the Gold's collision that might be useful when working with rigid bodies. Okay, well, actually, collisions are universal. They apply to any type of objects that you might want to use. Okay, so eventually you might also use collision with soft bodies. Okay, like textiles and so on. Tiziano, can I ask you to turn off the mic, please? Okay, thank you. So okay, so let's do. I divided this. This is basically the whole rigid bodies explanation. Basically, we will discuss all these group of components here, except from the beam. Okay, so the beam I will leave it as the last discussion here because it is the more complex. And actually, you will see what's the potential that this beam has, which is basically substituting the whole problem that we were discussing here. Because what we were doing here was representing a very rigid body using an elastic body. So we would be pushing the elastic strength and all the remaining forces to the limit, and that's why Kangaroo becomes very, very slow. Okay, but there is a different approach using rigid bodies in order to simulate, for example, a rigid objects like beams and so on. Okay, but we will discuss it here at the end of this section, which might extend to the second class. Okay, let's see how things work out. Okay, so let's deal with the first rigid body and with the first component that I'm going to discuss, which is the rigid set of points. Okay, which is this one. Now, what does the rigid point set do is basically take a group of points that you can define however you like, okay, and then say that the mutual distance between these points is not changing. So imagine, for example, that if we have this set of points, which is a planar set of points, okay, because it comes from a construction that I did with a polyline, okay, and you must imagine that these points are interconnected by a bunch of springs or a bunch of rigid bars, let's say so, which is basically this structure here. Okay, so for example, if we don't consider the diagonals and we consider the four sides of this rigid structure, this thing can shear basically. So for example, there is no anchor or no let's say restraint, okay, that will be avoiding this point from sliding in this direction, and then this let's say this quad here will compress in the cross direction. Okay, so these two diagonals here allow this object to behave like a rigid set of bars, and therefore the vertices will be basically maintained at the same distance, mutual distance. So this is the rigid body, the rigid point set component. And it also asks for a plane, but this is something that's optional, okay, because it says if you don't provide any plane, it will use the XY plane position in the centroid of your point set. Okay, you would see that this plane here appears in almost all the rigid bodies definitions. Okay, and we will discuss it later with more relevant systems. The other thing that I am using here is a simple anchor point. So you see that basically I have a set of 4 points, and I use it for building a polyline because this is the object that I want to see. It is just connected to the show component. The show component allows Kangaroo to show some geometry, some specific geometry that you want to use eventually after the simulation. Okay, so we will discuss this in a while because I'm going to rebuild these definitions, okay, together with you, so you can understand perfectly what's the workflow inside them. So I'm using this 4 points to display basically this polyline here during the simulation, but I'm also using this set of 4 points as a rigid point set, and I'm using each of them for specific, let's say, forces and simulation. For example, the first point, I'm using it as an anchor point. And the remaining 3 points, I am applying a vertical load to each of them. So basically, there will be one of the 4 point anchored to the ground, and the other 3 will receive a vertical load that will tend to move them in the vertical direction. So basically, what happens with this is that if I release the simulation, you see that this is what happens. You see the anchor point here doesn't move. The 3 points are basically being pushed up, but there is the rigid point set that basically simply avoids this object from deforming or stretching. Okay, so this behaves like a rigid quad that simply rises up because of the vertical load, and it's anchored to the ground because of the anchor point. Okay, so let's build it from scratch. So you see exactly how it is made. Of course, I will just build it from scratch in order for you to better understand how to build Kangaroo scripts. But remember that these, despite the fact that we are not talking about textiles and only about rigid bodies and tensegrity and origami, this is still a basic course. Okay, so I need everybody to understand exactly what's the workflow inside Kangaroo. So what I'm going to do, I'm going to replicate this situation here. This time I will do it a little different, okay, just so that we work with a different geometry, for example. So I'm creating a circle. I'm going to divide this circle into a number of segments. And then I'm going to use these points here for the simulation, okay? So what I'm going to do, I'm going to take these points and take, for example, I will do some kind of data manipulation as well in this case. So I will be, let's say, partition listing this set of points. And what I'm going to use one, the first point, I want to convert it into an anchor point. And then if I know how many divisions I'm giving to our circle, because this is defining the amount of points, okay? And I want the partition list is taking the list of points and splitting it into chunks. And the amount of points that are inside any of these chunks is defined by this size parameter here. So if I have 14 points and I want to isolate the first one, I pass 1 to the size, and then I need 13 more for the size of the second chunk of points. And 13 means basically subtracting from the amount of division the value that I want for the first chunk. And I plug this here. So what I'm doing, I'm defining basically two different groups of points, where the first will contain just one value, and the second group will contain the remaining 13 points. So here we have chunks will emit a data tree, which has one branch with 1 point, and the other branch contains the remaining 13 points. Okay, so I explode this tree, and I will have a branch here, which is a list actually with the first point, and the second branch contains the remaining 13 points. What I want to do, I want to convert the first point into an anchor point, and I want to apply a vertical load to the remaining points. Now, if we want, normally, this is also a good practice that you might want to implement in your definition. While elastic objects or rigid bodies and so on have a geometrical representation, you see a circle, you see the points, vectors and forces are invisible because vectors normally are invisible in Grasshopper. So let's say that we want to see in the vectors that we are applying to this system. You might want to use, for example, the usual z vector, because we want to apply some kind of gravity, be it vertical, be it positive or negative. In our simulation, it doesn't matter. So I will create this vector with a factor, and this factor is going to be like between minus 1.00, smaller than 0, smaller than 1, for example. So this is the vector that I'm going to use to displace the point that I can displace. But I want to see this vector in the preview, so I know what will be the action for this load. So what I'm going to do, I'm going to use a vector display, and I'm going to use this vector. I'm going to show this vector anchored to the points that will receive the vertical load. And so the vector that I want to show is this one. So if I do this right now, you see that I can show the vectors that I am applying to my points. And I also can recognize that this is the anchor point, okay? So this helps to understand what's going to happen during the simulation. So what I expect is that this rigid circle will rise here from the left and will just become vertical being anchored to the ground in this point here. Okay, so the vertical load is set, the anchor point is set. I just miss the rigid set of points. Now, the rigid set of points is not the chunks, is the whole set of points. Okay, so I take the points coming out from the divide curve and convert them into a rigid set of points. Okay, the plane, as you can see, is always barycentric, so it's placed in the centroid of this point cloud, basically, and everything works just perfect right now because we already have all the things that we need. I will grab a solver and a toggle. One consideration, I think I already said this in the webinar, but if you weren't there, oh, there is a chat. Sorry. What do you use inverter polyline component? Where did I invert? Okay, you are having some kind of lag, Joshua. Okay, let's double check. First of all, Tiziano, invert of the polyline component. I'm using an invert somewhere. I don't know. Maybe you were talking about the previous definition. Can you turn on the mic so I can understand what you are talking about?
Can you hear me?
Yeah.
All right. It was the previous definition, the one with 4 points. Since I don't know what
okay.
Let
me double check. Oh, it's not. Well, it's inverted because it's closed. So normally when you connect points with a polyline, it is open. But I needed a closed quad. So I inverted the closed. So basically, it's better to.
So it's the same to set the Boolean to true.
Exactly.
Okay. Yeah.
So you see.
Okay, I didn't know it.
Yeah. Here it is. So you see that it is closing the quad. That's the only reason.
Thank you.
You're welcome. And Joshua, you are having a lag. Anybody else is experiencing some lag with respect to my screen? I think Tiziano doesn't have any lag because it was almost in real time, the interaction. I don't know. I think Joshua, you have eventually some connection problem. So, but anyway, please, if you are experiencing some lag, it's better to. And also, if you have some question, I prefer you turn on the mic so I hear you because there is no sound from the chat window. Okay, so I prefer that you turn on the mic and then just ask and interrupt me. Okay. I was saying that during the webinar, I was using a plugin which is called false start toggle, which is this one. Now, I prefer to use this because I don't want Kangaroo to start automatically. I prefer to have all the simulation stopped by default. And the false start toggle is a plugin that allows the toggle to reset to false any time. And there is a link in one of my recording from the textile simulation webinar, where you can download the false start toggle. Okay, so just go to YouTube, find one of the tutorials or the webinars that I just published a few days ago, and you will find this plugin. So here I will plug the false, and then I need a button eventually to reset the simulation, and then let's plug all the goals to our simulation. I will turn everything off here, so you will see only the points for now, and then I will run the simulation, and here it is. Okay. Now, for example, you can see, for example, that this rigid point set is doing something weird. So what's happening is that all these points here are basically respecting the circular configuration, okay? But this point doesn't. Why? Because this point is subject to a force, which is the anchor point, which is very strong, okay? So when you work with rigid bodies, also if you work with a rigid point set, I do recommend that you increase the strength, okay? So eventually here we also have a strength of 10, and we are applying a load of 1. But consider this, if you convert this set of points into a rigid set, this point will be basically virtually connected to this one, and also to the other one. So basically, when you consider what load is being applied to all the structure of point, you could consider that it is 1 multiplied by the amount of points that you have here. So the whole structure is being pulled up by a total load, which is basically the amount of points, which is 13, multiplied by 1. So you have a load, vertical load of 13 applied to this structure of points. But their strength is just 10. So this point, which must be anchored to the ground, will stay apart from the structure. So I do recommend, for example, that you also provide a strength to the rigid point set. And you see that if you increase this, you will have a proper behavior for your rigid body. Okay. Remember that this rigid point set is dealing both with the anchor point and the load. So rigid point set is some kind in between the rigid bodies that we are going to simulate in a while and the elastic simulation that we just left a few minutes ago. Okay, so it's just a hybrid connection between the two worlds. But you see that everything is just working fine once we find the balance between the different forces that are playing a role in this simulation. And also we might want to use the show component, which I was telling you. You see that if you don't use the show component, Kangaroo will only display the goals that it is using. And now in this case, for example, we don't have any elastic connection between this point set. So the only thing that it shows, Francesco arrived. You see people. Okay, Francesco, let me salute you. Hi, Francesco, can you hear me? I really hope so. But anyway, you see that here we have only, Kangaroo is only displaying the points. And so that's why there is the show component, because Kangaroo will always work with springs and points, and eventually with mesh and this kind of objects, okay? So the only thing that you will get from the solver output will be eventually lines, will be meshes, will be points, and so on. If we want to see the original curve, for example, this circle here, and we want to show how this curve is affected by this deformation, we must use the show component. Now, if we plug the circle in the show component, you see that this becomes red, because the show component doesn't accept all types of geometries, okay? So if we use instead the divide curve and we create a polyline and we connect all these points together, and here it is, closed. Let's invert the closed, because actually it is false. We want it to be true. I do prefer, for example, this is something that is personal, okay? I could do this. I could do set Boolean to true, okay? And I have the closed polyline. And it's absolutely the same of inverting this parameter. But the thing is that I do prefer that everything is visible in the definition, in the script, because else I don't know what happened inside a component. So that's why I prefer to keep this to false and eventually set the invert option to operate on this input. So I know that something is happening in this component, okay? So that's why I prefer to do this. So yes, we have the polyline here, closed polyline, and I will pass it to the show component. And as you can see, the polylines are a type of geometry that the show component can accept. And I will pass this to the goal objects. And you see that now we have the representation of our polyline. You see that there is still some stretching, which was hard to see while working only with particles or points. So it means that we can also increase the strength of the rigid point set a little more if we want to get rid of this slight deformation, okay? But anyway, this is something that you can adjust accordingly. It's very easy at this point. So yeah, basically that's it for the rigid set of point. Now, The rigid set of points is something that we are using inside one single object, of course. But you can have several bodies behaving like a single set, a unique set of objects. So for example, if I say that, let's stop the simulation and reset it, okay? So this is the circle that I have here. And then what I'm going to do, I'm going to change things a little. So I'm going to create a circle by center and radius, okay? So I will say, I will give this circle 2 different points, like doing this, set multiple points, and I will pick 1 point here, for example, and another point here. So I have 2 circles. And I will give this circle a radius of, I think the original one was something between 5 or something. So I need 2 different radiuses. So I give 2 sliders here. So I have 1 larger circle and a smaller circle here. And what I want to do, I want the smaller circle to be at a higher level with respect to the bigger one. So I will take this point here, take the second point that I picked and move it up, and eventually from the top view, move it also like it is more or less concentric with the first circle, like this. Okay, it's not let's say, oops, sorry. I think I have to do this manually, because when you do this from the top view, everything is flattened to the ground, as you can see. And now, as the 2 points are coincident, it's very difficult for me to understand which point I am moving. Okay, so I do prefer to do this with the inside grasshopper. So what I'm going to do, remember that the second point is the smaller circle. There is no change in the order of data inside the grasshopper lists and data tree unless we want to change this order. So the second point would be associated to the smaller radius. I want to take the second point, so I go into manage point collection, take the second one, and instead of having 0, I will give a height of 5, for example, and okay. So you see that the smaller circle is higher than the larger circle. So I want to use these 2 here, and I plug them into the divide curve. Now,
Giancarlo, can you redo it? Because I didn't see when it changed the last parameters.
Yeah. So, yeah.
Maybe it's because also is okay. Now I see that everything changed, so it probably is the screen that moves.
No, actually, everything was disconnected from the divide curve, so there was no updating. The problem is that Kangaroo only updates properly when you pick the reset button. Okay, so until you pick the reset button, and I do recommend that you don't change anything in the geometry of your system while Kangaroo is running. So always set the toggle to false, be it the standard toggle or the false start toggle. Set it to false before changing anything in the geometry of your system. Okay, and then do the changes that you want, and then reset the simulation always before starting a new one. So in this case, what I wanted to do was increasing the height of the smaller circle. So I went here in the manage point collection, take the second point and change the z value of its coordinates, okay, to 5 or to whatever we want. So basically, this is the new height, and I want to take these 2 circles and create sets of points along the 2 circles, like this. So what I'm going to do right now, I'm going to work with 2 separate sets of points, and you see that I only need 1 anchor point. So the only anchor point that I want to fix to the ground is this one. So it's the first point of the first circle, while all the rest is must be part of the points that will receive a vertical load. Okay, so I have to change something here in the data manipulation section in order to do this properly. Okay, now what can I do in order to do this? Well, actually, we get here 2 branches, a tree with 2 branches, because we have eventually 14 points for the first circle and then 14 points for the second circle. So that's why we get here from the divide curve 2 different branches, 2 different groups of points. The first point, the first set of points belongs to the larger circle, because it was the first point that I picked, the one that's on the ground. And the second branch refers to the upper circle. So what I need to do, I need to take the first point of the first branch, isolate it, and use it as an anchor point. And all the rest must be subject to a vertical load. So I prefer, in this case, to flatten this. If I flatten this, I will have one unique set of points where the first point will be exactly the anchor point that I need. Okay. Remember that in Grasshopper, the order of data inside the groups doesn't change. Okay. So if I don't flatten this, the first point of the first branch will be the anchor point. If I flatten this, first come the first 14 points that are from the larger circle. So the first point will always be our anchor point. So what comes out from this 0 here will always be one single point, which will be this one. And this will be used as an anchor point. Now, the problem is that if I use the result of this subtraction as the size of the second group, you see that here we have several groups coming out, which are 113, 113. Why? Because we only provide two values, and the sum of these two values is not enough to cover the whole amount of data that we have here. Okay, so this size here, this subtraction that we did, cannot work with 14. Must be 14 by 2, because this defines the total amount of points that we have from the division of the two circles, minus the single point that I am going to use for the anchor point component here. So here we have 27. Here we have two branches, one containing 1 point and the other one containing all the 27 points. And we are splitting things properly right here. If we reset, we see that, well, actually, this polyline is no longer valid, of course, because I have flattened this. But in this case, for example, if I want to show the two circles and I want to use the polyline, what I need to do, I cannot flatten here. I need to flatten with a separate component. Okay, so I cannot flatten here because I need these two sets of points for the polyline to work properly and have these two circles here. And I can flatten the data after coming out from the divide curve and use it for the partition list. And also eventually for the rigid point set, like this. Okay, so it's just a trick in order to allow using both the polyline and also creating this kind of data manipulation properly. Okay, so I reset this, and what I should have right now is an anchor point here and all these set of points capable of moving up and behave like a rigid truncated cone, basically. So if I release the simulation, you see that this second circle here is being maintained like rigidly connected to the first one. Okay, so we have two separated bodies acting like one single set of rigid points. Okay, so you can create very interesting, nice, and complex simulation in terms of rigid structures. Okay, despite the fact that they are rigid bodies. Okay, we are only working with rings actually. Okay, but they are rigidly connected using this rigid point set, involving the whole sets of points coming from the two bodies. Okay, so imagine to extend this to eventually three-dimensional object. It's absolutely the same. Okay, so it's very nice to work with this kind of components here. So I will just group these and turn it off. And I will
really quick before we move to the other one.
Yeah.
Once, I mean, you set the 2 points manually in Rhino, and then you plug it just in the beginning. It's because once I set the 2 points in Rhino, and afterwards I plug the 2 radius, when I right-click to manage point collection, is grayed out.
Where are you? Where are you?
The first thing is there where you are. Okay, all right, okay. So you okay? My fault, my bad, because I press manage collection on radius. So
on radio. Oh, okay. So this is something that yeah, this is something that it has to do to how Grasshopper uses the so-called volatile data and fixed data. Okay, So basically, you cannot manage collection here because the collection is originated elsewhere, which is here. Okay, so this is just receiving the values. You cannot handle the values here. You have to handle them here or here. Okay, so this is something that it's a general principle in Grasshopper.
But actually, I don't know why. I also have gray out manage plane connection under P.
Here, you mean here?
Yeah, yeah. Okay, so you have to press. Okay, sorry. Yeah, you have to press the point. Yeah.
Okay.
Third one, I got it.
Okay, perfect. Okay, so I was saying I will create some kind of live exercises here. So this, for example, is going to be the first exercise, and I'm going, as always, to use a jump. So I will use a jump connector, just connecting these, which was the standard example that I already prepared, and a different application here in order to for you to jump to the correspondent exercise. Okay, so you will have the general application here, and then you double click here, and you go exactly to the exercise. Okay, so let's move on and let's start talking about the, well, I would say the real rigid body simulation. Which starts from this small definition here. I'm going to show you how this part of the definition works. You see that there is one huge group, okay? Because I didn't want to create, it was boring to create one solver per each script. So I just create one single solver, and everything is connected wirelessly to this set of things here. So every time you want to work with one part of the definition, you just plug the correspondent set of data to Kangaroo. Okay, so I will come back to this in a while. Okay, so now what we were about to discuss is basically our first real rigid body simulation, which is basically these two boxes here. I'm going to use this component, which is called align faces. Okay, so this is very nice when you have to simulate some lining up of several different solid objects. Okay, so you will notice that there will be no elastic force in this simulation, not even by far comparable to the elastic simulation that we ran at the beginning of this section. So what happens in this, as always, a quick explanation. So you will see that there is a rigid body definition. A rigid body definition, which is involving the two boxes. So there is this object here, which is not basically by itself, it doesn't do anything, okay? It just converts any object that can be a mesh object or a B-rep object, which is basically a Rhino standard definition for a solid. So a closed B-rep is basically a solid object in a NURBS object in Rhino. So you see that this rigid body here accepts both mesh or B-rep. Okay, so in this moment, I'm using some boxes. Okay, so they are closed B-rep. But you can also convert them into mesh if you prefer, and then plug these meshes into the part for the rigid body simulation. And you see that, as I was saying, when you work with rigid bodies, you always have this plane input. Okay, now this plane is something that it might be misleading somehow, confusing somehow, because in some components, like for example the align faces, one could by mistake interpret these planes here as the planes that you want to align, but it's not like that. Okay, so we are going to discuss this in a while when working with the align faces. So just focus on the rigid body for now. This is the way that Kangaroo converts any object into something that doesn't deform at all. Okay, so there is no elastic property for these objects here. They cannot deform during the simulation. So basically what happens here, we have the first box, which is the big box. Then there is the smaller box here on one side. These two boxes, we are evaluating one of their faces, which you can see here. I'm selecting the upper face of the first box, the upper face of the second box, And then I am creating a frame along these two faces here. And these frames here will be used as the faces that we want to align using the align faces. Okay, so as always, let's repeat this here on one side. I'm going to use a different set of objects as always. So we will have a different setup. Let me prepare things so everything will just work fine. You see that the align face is actually connected to the bouncy solver. So this is the preview of our first setup. So what I'm going to use right now, well, actually, I would like to use a more complex solid, but I don't know if you have the plugins installed. Well, I will just tell you quickly. You might have, for example, the Lunchbox plugin installed when you have these mathematical solids, which are the icosahedron, for example, the dodecahedron, for example, and so on. Okay. What I want to have is lots of faces available. But if you, in case you don't have the Lunchbox plugin installed, what you can do, remember that rigid body can work with both mesh and B-reps. So eventually what you can do is create something like a mesh sphere. Let me grab the mesh sphere. You see that there are a couple of mesh spheres. These are not, let's say, provided by any plugin. These are standard Grasshopper component. So you can take, for example, the standard UV mesh sphere, not the mesh sphere X. So let's grab this one. Let's say that it has a smaller radius. So we have things under control. And we want to use U count and V count with also smaller values. So basically what we get here is like let's control M to activate the edges. So you see that we get this kind of platonic solid or something like the ones that are available inside Lunchbox. The only difference is that in this case, this is a mesh object. I don't care actually about the actual shape. I don't want it to be a sphere. I want it to be a polyhedron, okay? So this is the mesh object that I wanted to have. You see that it has triangular face as well as quad faces. But as we are working with rigid bodies, it doesn't matter at all, okay, what type of object do we have here. So we go into the 6 degree of freedom set of components and we grab the rigid body and just plug this here. And you see that automatically there is a plane showing up, which is basically the plane aligned along the XY direction and placed in the origin, well, in the centroid of the barycenter of this mesh object. Okay, so as this is a spherical object, basically, and it has a polar symmetry, the plane is set in the origin of the XY system. But if we change the base plane of our sphere, this plane will move accordingly. In case you want some additional points to be attached to this body, to these rigid bodies, you can define it here. So let's say, for example, let's do something like, well, it's quite useless. It's just for showing how this rigid body works, okay? So let's say that I take a NURB sphere, in this case, and I say this NURB sphere, you have a larger radius than the mesh sphere that we have created, like, for example, this. And I don't want to use this sphere in the simulation. I just want to populate this geometry with random points. Okay, so let's say that I want these points to be rigidly connected to the inner mesh sphere. And then I take these points here and plug it into points. So when the rigid bodies moves during the simulation, all these point clouds surrounding the rigid body will move accordingly. So if this inner mesh rotates, the whole point cloud rotates. If this rigid body moves, the whole cloud of points moves accordingly, okay? So this is quite important, quite interesting in case you want to simulate some kind of, let's say, complex object, but you don't want to model the whole object before the simulation, okay? Having this set of points means that this set of points will also be available after the simulation. So you can isolate the points and eventually manipulate them after the simulation in order to react to the rigid body moving, also from a geometrical point of view. So let's say you want to connect each of these points to the surface of this mesh object. You can do it after the simulation instead of before the simulation. Okay. But anyway, this is something that eventually we might want to take a look at it later on. I will leave it off by default for now and disconnected from the rigid body. We already have everything that we need here. Okay. Then there is the strength. But this strength, you see that normally when you don't work with real life forces, it's sufficient to maintain this object as a rigid body. Okay, to don't have it deformed during the simulation. And so this is basically the first one. And what I need to do right now is basically take one of the faces of this object, because we want to work with a command which is called align faces. Okay. So you see that, first of all, you see that there is basically no information in the align faces regarding the rigid body. Okay. Align faces doesn't want to know what rigid body you want to involve in this goal here. So you can see, for example, that also in this example here, you have the rigid body not connected to the align face and not connected to the align face. The rigid body is a goal that goes straight into Kangaroo solver. Okay, so even in this case, for example, you see that when align faces asks for plane A, he wants to know what's the frame of one rigid body, not what rigid body you are using. So it's the plane that must be connected to plane A. Okay, so this tells align faces that we want to work with these rigid bodies that has this orientation. So the planes in rigid bodies are important because they define the orientation, the original orientation of the rigid body. Okay, so what we need right now is a different object. I will take another mesh sphere and would take a point, set one point, and take the sphere away from the previous one. So we have a couple of mesh spheres which are identical, so they are basically polyhedra. And I will grab another rigid body, and I will then have a different plane that I will use as plane B. Okay, that's it for the rigid body definition, because eventually we will use a data container in order to pass all the goals to our Kangaroo solver. Okay, but here I'm going to replicate this as an exercise, so I will be using eventually a bouncy solver by itself and a false start toggle. Let's prepare this in the meanwhile, and a button. Eventually later I will copy paste this in order to avoid this kind of construction. Okay, so first of all, the rigid bodies are already goals for our simulation, and then now we are going to populate the parameters for the phase A and phase B. I do recommend always that when you work with Kangaroo, you keep off everything that's on the left of the solver. Okay, so you only see the preview of the deformated system. Okay, so phase A and phase B, these are the two phases that we want to align for our objects. Okay, so let's deconstruct these meshes. There are a bunch of commands that you might want to use. I'm trying to keep it simple and use only standard Grasshopper components, but Kangaroo too. Okay, of course there are many plugins that provide functions that gives you access to directly to the faces of your mesh. Okay, but I don't know if you have these plugins, so I will be using only standard Grasshopper components. So let's say we want to start with the second one. So this is our deconstruct mesh, which is basically an explosion of the mesh. Now the problem with deconstruct mesh is that it doesn't provide access to the real faces. The result of faces is the connection scheme by which you have to connect mesh vertices in order to obtain each of the faces of the mesh. So for example, you see that faces outputs, the first output is T, which means that the first face is triangular, and it's obtained by connecting vertex number 0 with vertex number 2 with vertex number 1. So if you take the vertices here and you take a look at these with a panel, you see that these vertices here are a list of points, and as they are in a list, they have an index number. So what faces is saying is that if you want to obtain the first triangular face, you must connect the point 0 with point 2 with point 1. If you do this, you will get the first triangular face. And you see that, for example, the last of the queue that you see here is 6, 7, 11, 10. So you must connect 6, 7, 11, and 10 in order to get to that quad face. Now, how can we access the faces of the mesh while we have this connection scheme? You can do it like this. There is another component which is called deconstruct face, okay, that takes this scheme here and says, okay, the first corner of your meshes are these indices here. So if I take a list item of the vertices and plug corner A, now what I get from here are all the first corner of our faces. If I take another list item and use corner B, these are the second corner of each face. And then corner C, and then corner D, okay? So now we have, let me turn off the solver as well. We have separated sets of points. They correspond to each of the 3 or 4 corners of each face of our mesh object. Now, we are not dealing with elastic deformation, so there is no need for us to have, let's say, mesh faces. Once we have the 4 corners, for example, of this face here, we can use these corners to build a 4-corner surface or a 4-point surface instead of a 4-corner mesh. So I can use a 4-point surface in order to create a surface from corner A, corner B, and as soon as I plug corner C, I already have triangular faces here. Of course, when I plug corner D, I only get quads where there is the 4th point. There are some triangles here, so we will get eventually triangles before plugging the 4th corner. You see that the poles always have triangular faces because we were working with a originally with a UV sphere, okay? So in this case, when we plug this, we already have the surfaces. So we have 16 surfaces as we had 16 connection schemes here between triangles and quads, okay? So this is just a trick to switch between a mesh object and a NURBS object by working with deconstruct mesh and deconstruct face. So once we have these are untrimmed surface, which is quite important when you work with this kind of components here, like, for example, the evaluate surface that we are going to use. It's important to have untrimmed surfaces, okay? Because when we plug this here, and we reparameterize these surfaces because we want to evaluate them in the center of the surface. And the center of the surface, if we reparameterize each surface, it means that the surface, once it is reparameterized, will measure 1 by 1. So if a quad measures 1 by 1, its center point will be 0.5, 0.5. So we can use an MD slider like this one, which already comes with a 0.5, 0.5, in order to access the center frame of each face, okay? Now, this frame here will be our face A or face B. In this case, it's face B because we started from the second mesh, okay? We don't want to work with all the faces. We just need one face. This is the face that we want to align with the face belonging to the other object. So I will take, for example, this set of surfaces and take, for example, list item and isolate just one face, say this one, okay? Whatever, it doesn't matter actually. And I will evaluate only that one. Now it's important to understand that once we evaluate this particular surface here, we get a frame, and this frame has an orientation which is defined not, well, X and Y axes are mostly irrelevant because they are generally aligned with the face. The problem might be the Z axis. This Z axis might be flipped. So it's important to understand that according to the direction of the Z axis, this will affect the lining up of the two rigid bodies along their faces. Okay, we will see this in a while. So let's say that this is the face that we want to use for the second mesh.
Sorry, Giancarlo.
Yeah.
Sorry.
Yeah.
If I don't have the Z axis, because I can see Y and X. But
okay. This depends. This depends on Rhino. Okay. You see that now I'm in wireframe mode, and I also see the vertical Z axis, the blue axis here. And as a result, I can also see this one. But this is something that has to deal with the settings of the display options. Okay, so you right-click on the actual viewport, name, and you right-click and then select the display options. You go straight into the wireframe settings, which are the actual settings for this viewport. And here you will see that there is the grid option. And this grid option has the show Z axis activated. In your case, it might be off. Okay, so you have to activate this, and you will see the Z axis appearing also in the frames coming from Grasshopper. But it's just visualization, okay? But it's important because in this case we want to consider what's the orientation, the proper orientation of our frames. So let's say that this is frame B, face B actually, okay? So we already have it. Now let's repeat this, all of these. I will just copy paste it and use it for the first mesh, which is this one. Okay, so I plug the first mesh here, and you see that I also have the same frame. Now I don't want to work with the same frame, so I will go into the list item here, which is isolating the same face because they are the same order. It's basically the same mesh, just displaced in a different position. So it's normal that the first face will be coincident. So I have, remember we have 16 faces here, so I can take a slider between 0 and 15. This is not exactly parametric. If I change, for example, the resolution of our meshes, this slider will be not enough eventually. But for now, it's more than enough. I just can change the face that I want to align with this other one. Okay, so I simply change this to 10, for example, and then I have this face here. And so I have the frame for object A, which is face A. Now, everything is set for these aligned faces. Flip will eventually reverse the relative direction of the planes. This is important because in case you have some flipped planes, you will have basically the opposite aligning of your faces. Okay, but this you can only understand it, or I would not spend time by trying to understand if things will work properly. I just prefer to run the simulation right now and see what happens, and eventually decide if I flip something here, for example, or I flip something here from the frames coming out from the evaluate surfaces. So this is the goal, ready, and I will plug it into the bouncy solver, okay? So when I run the simulation, what I should see is this. Now, how do we recognize these faces, basically? So what I'm going to do right now is I want to, let's say, visually recognize these two faces that I am selecting here at the bottom. If I turn on the preview, I get the faces before the deformation, okay? You see that there is a quad here and a triangle here, okay? And you see that faces now are lining up in a very strange way, like in diagonal, okay? Now, this is because the aligned faces doesn't care about constraint, okay? The only thing that it does is moves and rotates rigid objects in order to align the selected faces, okay? So it doesn't obey to any constraint unless we specify that there are some constraint in our system. Okay, so as we are not working with any constraint, there is no anchor point and not even a support, for example, that we will see later, then these two objects are free to move in the space. So the only thing that matters here is how these spaces get aligned. Now, how can we isolate and make visible these two faces? Well, we can do this by creating, for example, a show object and see. If I select the list item, which is a surface basically, and I plug it here, you see that it becomes red. But what I can do is create a mesh surface. So convert the actual triangular surface into a mesh object and pass it to the show. component. You see that show accept meshes, but not surfaces, okay? So if I repeat this with the second phase, which was from the other object, this one, and I plug it into the show component, and now I plug the show component into goal objects, you see that these are the two objects here. You see that they still do not interact with our object. Now, what we can do here, in this case, in order to have a display of the faces that are involved in the align process, we must work with the output, because there is no way in this moment to isolate these faces like meshes. Or one thing that we can do is like this. Before the simulation, we have access to points for the rigid object, for the rigid body. Okay, so once we have the, in this case, it's not relevant to have the mesh objects. Okay, once we have the two list items, so we have the mesh, the surfaces here, and we evaluate the surface in 0.5, 0.5, we have not only the frame, but also the center point. So the point that you see here is the centroid of the two faces that we selected. Now, this center point here belongs to the second mesh, so to the second rigid body. If I take this point and use it as points to be rigidly connected to our system, let me stop the simulation for now. You see that these points belong to this triangular mesh here. It is its centroid, okay? And also I can do the same with the second point and plug it into the points of the first rigid object, which is this one. And so if I reset, you see that I have one point appearing on this face here and one point appearing on this face here. These are the two faces that I want to align. Now let's run the simulation. You see that here there is something that becomes starts to act weirdly, because what happens is that we also have, in this case, points involved rigidly connected to this face. Now, as the point is coincident with the face, there is a rigid situation where we have a face that cannot deform and a point that is a rigid point. It cannot be coincident with this face, because in a rigid body, two parts cannot be coincident in the same point in space. So that's why Kangaroo, what it is doing right now, is trying to basically conciliate this position here, and therefore it starts to separate the object like in an elastic way. So you saw that the object started bouncing around. This is the solution that Kangaroo starts to implement, okay? But we can also do something like a little more intelligent. We can move, for example, the point that comes from this evaluate surface in the normal direction directly. Now, the normal direction is a vector which is perpendicular to the surface and measures 1, okay? So if I go and stop the simulation and reset it and take a look at this, you see that I am taking the point lying on this surface and I'm moving it outward with a distance of 1, okay? And if I do the same with the first mesh, or sorry, with the first face that we isolated, you see that we have this point here. Now, instead of plugging the original point, I will plug the displaced point into the rigid body. So this is the point from our for our first mesh, and this will be the point for our second mesh. And let's see if things work a little better right now. Yeah, it tends to work properly, but you saw that there was still a little, let's say, interference between the two objects. They were quite close, but you see that in this moment we start to understand what are the two faces that are aligned, okay? So it is this square face here, or this quad face here, with this triangular face, okay? So these are the two faces that are getting aligned by these aligned faces. Now, of course, we also are leaving these two objects free of moving around, okay? But these are rigid bodies, okay? So let's say, for example, that I somehow maintain these two objects fixed in one point, okay? So for example, sorry. So for example, I will take one of the vertices of our mesh and use it as an anchor point. So the two objects will be free of somehow rotating, okay, in 360 degree with 6 degree of freedom, basically, but one of their vertices will be stuck to the ground, okay? So what I'm going to do, I'm going to use the deconstruct mesh that gave access to the vertices for both objects. And what I'm going to do, I'm going to, for example, take one vertex of these two meshes here and use it as an anchor point. So I'm going to take an anchor like this, and I'm going to, for example, I don't know, yeah, let's say a list item. I don't want to use any plugin here, so let's keep it simple. So this vertex here would be an anchor point. We can also use a slider. We have how many vertices? 14. So a slider between 0 and 13. So we can change what is going to be the anchor point, like, for example, like this one. Okay. And let's repeat this for our second or first mesh, actually. So I'm going to use like this point as an anchor point. Okay. And so this will also be an anchor point. I'm going to move all of these thing in another position. So we have the anchor points here, and I will pass these anchor points to the goal object and turn off the preview of our deconstruct mesh. So if we reset the simulation, yeah, we start to see that the objects start dancing around, trying to use the anchor point as fixed point, but it is too strong to keep them in place, okay? But yeah, the important thing in this moment is just to understand what are the phases that we are using. I do prefer, in this case, for example, for these reasons, to work with the output. That's why I was mentioning the output, okay? So let's see how simple it is to work with the output in this case if compared to the problem that we get from the rigid points connected to our meshes. So what I'm going to do, I'm going to get rid of these points here. Okay, so I reset, I no longer see the points. And if I do this, you see that also this rigid situation here is stronger than eventually the anchor point that we are defining for our meshes. So it's not, let's say, an effective way of working this one with the anchor point. I will leave it like here off. So eventually you can play around with this. And also I will leave these points here like grouped and off if you want to play with it by yourself. But I do recommend that you start working with oh, sorry, no, I cannot turn everything off because I was also creating the frames here. So this is something that stays off. The rest is necessary for defining the phase A and phase B that I want to align. So let's see how we can deal with the output. Now the output here, it's important to understand also how the output works. So you see that the output, we were mentioning it during the webinar on textile, always contains some null objects, and we must get rid of them. Now, where do these null objects come from? Well, they come from the goals that we plug here, those goals that don't have any geometric output. They convert into null object. So for example, what do we have here? We have rigid bodies. They have a geometrical output, which are the two meshes, okay? While the align phase is just a goal that applies a force to the system in order to move geometry, but it doesn't produce any geometry, okay? So in order to keep it clear and to work with the output properly or in an easier way, what we can do is basically group the goals by type of goal, or also by type of geometry, okay? So for example, rigid bodies in this moment are working with solid shapes, okay? So their output will be exactly the same input that we are using, which is a mesh for both of them. So let's say that I create, for example, an entwine. Entwine allows to merge several workflow or several data flow into one unique data tree. So for example, what if I take the two rigid bodies and plug them into the branch 0, 0? Okay, so you see that the first branch 0, 0 contains two objects, which are the meshes. And then I take this goal here that doesn't produce any geometric output and plug it into branch 0, 1. And also I get rid of branch 0, 2 because I don't have any other goals that I want to use, okay? So I am grouping the goals by their preview, basically. And then I plug the goals here. Now, this is important. This is one of the things of the main differences between Kangaroo 2 and Kangaroo. Okay, this is important because one of the main differences between Kangaroo 2 solver and Kangaroo 099 solver is that the solver in Kangaroo 2 also accepts data trees, while Kangaroo 099 doesn't. Okay, so these allow a better organization of the goal when connected to the goal objects. Now, if we do this, what we get from the output is this. We get two meshes and a null object. Now, if we take a look at this, we get this. Oh, actually, I think that in this case, with this type of goal, you see that we get this list of objects here, but we must reconvert this list of objects using the same structure that we have here. There is a component here in the set tree group of component that is called match tree. Okay, so if I take this tree, which is basically a simple list, and I give this data tree, initial data tree as a match, you see that we get in an error. Input trees must have equal number of paths. Okay, so I cannot use it like this. So I need to manually rebuild the structure of this initial data tree here. So what we can do here is basically use a tree statistics. These tree statistics will give us the paths of the original data tree and also the amount of data contained inside each branch. Okay, so if we have these, we can also use simply a partition list. Remember that the way that data is sorted inside a group doesn't change. So if we have the first branch here containing the two meshes, and then we have the second branch with the non-geometric goal, we will have the first two meshes here and then the non-geometric goal which converts into a null object. So if I do this and use the length as size, now we get back to our data tree, okay, exactly as it was before the simulation, okay? And now we know that as we plugged all the relevant geometric input into the first branch, when we work with this data tree here, we only need to explode it, explode tree, and only work with the first branch because it is the relevant branch of our data tree. These are the two meshes, okay? So no matter what you plug inside this entwine here, just if you keep separated the geometric output that you need after the simulation in a separated data tree branch, then you can simply isolate it using a partition list and using a tree statistics, okay? So here we have the two meshes, and what we're going to do is use exactly the same method that we used here. Now, we took the mesh, exploded the mesh, built a surface for each face, isolated the face, and evaluated that face, okay, in order to have the frame. Now, if we repeat this, okay, if we repeat this after the simulation, using these meshes here, they are two, okay? So I need to dispatch them in order to have them one per channel. And then I'm going to take list B, for example, and take a look at this frame. You see that this is the actual position of the frame after the simulation. So for example, I also have this face here, which is the original face after the simulation. So if I take a look at the output right now, I also have a surface which lies here, which is saying which of the faces is being aligned. And you see that is this one with this one. If I repeat the same process for the list A output, like, well, actually we don't need to evaluate it because we just need a visual reference here. And I take list A, you see that we have our faces, we need to change here the index, of course. So the index that we were using here one was 10 and one was 0, okay? So 10 was for the first object. So the first object here is list A, so I am using here a 10 value. And here we have the face that is being aligned with the other one. Okay, so in this case, you see that working with the output is easier because you can simply isolate the face after the simulation without having to understand what is the face before the simulation. Okay, so eventually you can also turn off the preview of the solver, and you will see how these two faces here start to rotate and move in order to align mutually. Okay, so this is the effect of the align face. You see that it's very interesting to work with it. It produces a very particular behavior for our object. Not always it's easy to work with it because you have to put constraints in order to avoid your rigid bodies to dance around freely in space. Okay, so you have to put some anchors or some constraints like supports and so on. We will discuss supports in a while, okay? But anyway, you see that these got a little more complex because of the my will to don't use basically plugins, okay? If you use plugins, all this method of reaching one of the faces is easier. So you can also use one single step in order to access one particular face of your mesh, okay? But anyway, I will keep it Tell me.
Which plugin are you thinking about?
Well, there are many plugins. It's basically almost all the plugins that allow to work with mesh objects allow to explode a mesh into faces directly. I don't remember, but if I quickly use, for example, mesh explode here, mesh explode here, you should get explodes each face of a mesh into a new single faced mesh. Exactly this one. Now this object here is from it's a VB script. It detects it as a VB script, of course, because this is a custom component. But this custom component belongs to a plugin that, forgive me, but it's not that easy to understand which plugin it was. I have one plugin which is Mesh Plus, and here it is. Okay, so this is called Mesh Plus, OM Plus. You can search it on Food for Rhino. It's called Mesh Plus. It has several tools to work with meshes, also creating some complex behaviors. But anyway, it's just a function like there are many others in other plugins. This is just the first that I remember. Okay. But basically, almost all the plugins that work with mesh can do this kind of operation. Okay, just pick one and you will see. So I will deactivate this, move it here in the exercise section, and just take a quick look at how this works. It is already plugged to our solver section here. It only takes these two curves and aligns the upper face. Okay, so if I turn this on, you see that this is what happens. It's quite easier, of course, because they are just two boxes and two flat surfaces on top. So you have only a mutual slicing, vertical slicing of the two boxes until their upper face is aligned. Okay, you can use it in order to simulate complex rigid systems where you need something to be aligned. Okay, but it's difficult to talk of these things like in this abstract way, but you have to think that apply this into a complex system and you will surely find some application. Eventually, I will try to develop some kind of complex scenario and propose it like at the end of the course in order to examine basically it comes to my mind it could be a mix between a tensegrity and also an align phase situation, but I will see that. I will see. Let's see what happens. And let's skip to concentric. So I will plug this here, and you see that everything becomes orange because the section of concentric, which is this one, is turned off. So I will activate it and reset the simulation. Okay, so what happens here? I have two rigid bodies, once again. But this time I have a tube and a cylinder. And what I want to do, I want this to be concentric. So basically this small cylinder must be inside the tube, aligned to its center. So it's the same thing, basically. Now, the problem is
that we don't have a polyhedra, for example. So in this case, we have round surfaces. We must do something in order to understand what are the planes for our concentric input. The rigid body works exactly the same. Okay, so it's absolutely the same. You see that I have created this basically volume and XY plane aligned with the centroid. Okay, this is an explicit way of using the plane of a body. Now, why am I doing this? Because I might want to change the position of the plane of the rigid bodies. The plane of the rigid bodies, which is something that comes out naturally from here, and you will see that it is absolutely identical to the plane that we are creating here. You see that they are perfectly coincident. The plane of the rigid bodies gives this concentric component, as well as the aligned phase component, gives the reference of the rigid body in order to understand what part of the rigid body we want to align or we want to convert into concentric. Okay, so for example, I did it explicitly because I will use this method in order to work with this concentric component. And then the result is that when I run the simulation, these two cylinders start to dance around until they become concentric. This is very interesting when you work with some kind of mechanical design, for example, or you want to align the center axis of this longitudinal direction, for example. Okay, so it's quite interesting to work with concentric. So let's repeat this and let's work with. Well, I will work with the same geometry just in order to understand what happens if we have a different positioning for the center frames. Okay, so for example, what I did was calculate the volume of these and they use the centroid for the XY plane orientation. Okay, but I don't want to do this. What I want to do, I want to let's say let's do something different. Okay, just using standard grasshopper components. So I want to work with a random point inside this object here. So instead of working with the volume, I would use, for example, the populate 3D. Okay. Now the populate 3D, if we use a tube, for example, we'll use the corresponding bounding box. Okay. So the problem is that not all the points are inside our B-rep. Okay. So what we can use is a component which is called point in B-rep. These understand if a set of points lies inside or outside from a boundary representation. Okay, so when you have inside, you will have true. When you have outside, you will have false. Okay, so it's very easy to, for example, isolate with a call pattern, isolate only the points of this population that corresponds to this criteria. So here we have the points. We are calling the points that corresponds to the inside condition. And we are just maintaining those points. So you see that now we have only internal points. And what I want to do, and as the populated 3D is a pseudo-random component, I will be discussing randomness in the next webinar. I don't know if you are aware of it, but there will be a free webinar next week. So you are all invited to assist. So this is a random component. So the way that these points are sorted inside this object is totally random. Well, let's say totally, but it's not like that. But anyway, let's consider that it's absolutely random. So if I take, for example, a list item, I am picking a random point inside this tube. Okay, and I want to use this as the origin for my XY plane. So now we will have also the occasion to understand what's the meaning of this XY of this rigid body plane. So if I take the rigid body definition, the part that I want to convert into a rigid body is the B-rep, and I want to tell this object that it's the initial frame of the body is not the standard centroid, as you see it appears here, but it's this one. Sorry, it's this one. Okay, so you see that now planes is no longer visible here because it is coincident with this one. In fact, if I turn off the preview of this XY plane, this stays visible because it's the actual plane of our rigid body. Okay, that's why I was using that text structure. I wanted to edit the position of the rigid body plane. And if I repeat this with my cylinder, and I use also the cylinder like here for the inclusion and also for the rigid body conversion, you see that now we have this different position for the plane. And I can also use, we have a list of 64 points here. I can use a slider, well, I want to exaggerate between 1 and 10, okay? I need one different point, okay? So you see that each one of these values gives us a different point. Sorry, I saw someone was entering the meeting. I don't know who it was, but anyway, it doesn't matter. Paco. Yeah. Okay. So, well, actually, these are the two rigid bodies. As you can see, there are two frames in a totally, well, pseudo-totally random position. Okay. So now what we want to do is use the concentric. So concentric asks, what is the plane A and plane B? Now, plane A and plane B are coming out from the rigid body plane because I am defining that plane by our XY plane. So I can also use plane A and plane B coming from the rigid body. Now, concentric also needs what axis is going to be used as the longitudinal axis. And then once we have this list item here and list item here, which are 2 points, you see that axis A and axis B are asking for a line. You can recognize the black hexagonal icon. This is the symbol for lines. So I can use an SDL line for this, starting from this point. So I get this vertical segment here. I want to use a vertical longitudinal axis, of course, because this is a vertical tube and a vertical cylinder. And I can also use a SDL coming up from the other random point. So I will plug this line into axis A and this line into axis B. And now everything is set. I have the concentric goal ready to work. And then what I'm going to do, I'm going to copy paste whatever solver I have already here, disconnect all the actual goal, turn it on, and plug the concentric goal here. And what I need to do also, I need to plug the rigid body to the goals as they won't be taken into account. Okay, so if I run this, you see that now these two objects are getting concentric according to the planes that we have defined. So remember that this little cylinder had a plane here in this area, and this large tube had a plane here in the bottom area here, in this part of the wall. So that's why we get this, let's say, concentric relationship, which is not concentric, evidently, because we are not using the central axis of the two shapes. Okay. While if we don't plug this plane here, and we don't plug this plane here, it will be using the, well, actually, we are still working with these lines as longitudinal axis. So these two lines here alone are telling that the longitudinal axis still lies in with correspondence to the these points here. Okay, so if I do this, I am still displacing the two objects according to these lines here that lie on the outside, basically, of the shape. You see that this one lies in this non-barycentric position, and this one lies in this part of the wall of the tube and not at its center. So if we want them to be concentric, in that case, we might want to use exactly a vertical line starting from this plane here. So if we want to keep concentric, these two SDL line could also start from this plane and this plane here. So you see that now everything is back to normal. Okay. So yeah, basically that's how the concentric work, and that's the only thing I wanted to discuss was exactly the importance or the value of defining a specific plane for the rigid body. Okay, that is going to be the reference plane for any transformation that occurs during the simulation with any rigid body simulation. Okay, so just keep it in mind. It was the right occasion to discuss this. I will turn this off and deactivate this simulation here, move it to the exercise area, and plug a jump from here to here. Okay, so we also have this connected. Did I put a jump to the second one? No, I didn't. Okay, I will do it right now. So let's turn this off again, and let's place another jump like from here and belonging to this group, and this one is belonging to this group. And this is going to connect with the second exercise here. Okay, good. So let's switch to the third component that I want to discuss. In this case, I am taking back the rigid point set, which we analyzed at the beginning of this class. It is part of this group, so I wanted to point out what's the general behavior of this rigid point set. I'm going to activate this, and this is basically let's say a pseudosphere falling to the ground. Okay, now why I am considering this? Because when you work with rigid object, normally you don't want to work only with, let's say, aligning the faces or making few objects or a bunch of objects concentric and so on. You want to calculate collisions. Okay, so in this definition, what I'm going to do, I'm going to convert this sphere into well, let's call it sphere. You see, it has very few sides, but anyway, it's a mesh sphere, so it's a polygonal object. But anyway, I'm going to make this sphere fall down due to gravity and then, let's say, bounce on the floor. Okay, so you see that there are three goals here: the rigid body, gravity or vertical load, and the floor. This is the collision object. Okay, actually, this is the only collision object that doesn't belong to the 6 degree of freedom or Gold's collision group. Okay, you find the floor inside the Gold's point. It's here. Because in Kangaroo, the floor affects all the particles or the points that are involved in the simulation. Whatever rigid body or elastic system generates that point will be affected by the floor. Okay, so that's why you find it into the Gold's point. No point is capable of passing through the floor, and the floor is the XY plane. So it's this horizontal grid, basically. We will see that this is not the best way of, let's say, creating collision planes. This is a very standard way of creating a collision plane, okay, which is, by the way, the XY plane. We will discuss this later on. But then if I run the simulation, you see that this object falls down. It still has some elastic behavior, as you saw, okay? It still has some elastic behavior because this rigid point set works with a strength, okay? This is something that you have to deal with every time. So when we work, for example, with the floor, if we don't give the floor enough strength, points coming from each object of your simulation will be more or less capable of passing through the floor. So for example, if I disconnect these, the floor has a strength of 1, okay? But then we will have gravity of 1, a load of 1 applied to each point of our mesh. So we have a global load of 22 applied to the whole object, okay? So this is stronger than the resistance of the floor. And then you see that the object tends to pass through the floor. If you see it into the front viewport, you see that we are lower than the x-axis in this area. Okay, so you need to increase the value of the floor. When you have collisions and rigid objects, you don't want any deformation to occur, and you don't want a constraint to be more or less valid. Okay, if you have a floor, nothing can pass through the floor, and then you give floor quite a high value for the strength. This strength is actually stronger than gravity, so it's enough to avoid that these points get pulled lower than the frame. okay, the floor, sorry. And then there is the rigid point set. This rigid point set must be stronger than gravity and floor in order for this to behave exactly rigidly. So if I don't use this, you see that this object starts to collapse in this lower part, okay? Because this lower part is actually being, let's say, affected by the rigid point set strength and also by the load and the floor. So if you want the rigid point set to maintain its rigid aspect, then you must increase the strength. And normally this value must be higher than all the other values, okay? Because this rigid point set is not a force that it's pushing the points, let's say, through the floor. The load is pushing the points through the floor. So the floor must be stronger than the load, and the rigid point must be stronger than any other force present here. So that's how you establish an equilibrium between the strengths in your Kangaroo goals. Okay, and then we have this show here, which is only taking the mesh and pass it to the solver in order to have it visible after the simulation. Okay, so this actually doesn't deserve any additional example. We already made a quick example of the rigid point set at the beginning, and we also created an exercise. Okay, so yeah, basically we don't need any further discussion for this. I will eventually skip it right now. And then let's start with something which is more relevant, like solid collide. So I told you that, I told you that solid by themselves, well, actually are not that relevant. I mean, if you have solid things, you might want to have solid collision. Okay, that's mandatory. So in this case, for example, let me double check. Oh, sorry, I plugged the solid collide. No, I wanted to plug all the goals. Okay, so what we have here are two boxes, one on top of the other. Okay, and what is going to happen is that these basically this is the first box, and this is the second box. Okay, you see that there is basically a load applied to the first box. So the first box is going to be pulled down because we have a negative factor for this unit C force vector. Okay, so this box is going to fall down, and along the way is going to, let's say, is going to collide with the lower box. You see that there is this overlapping here in this corner of the two boxes. Okay, so while this object is falling down, it will collide with this second box, and this second box will be displaced from this original position. Then there is a floor. Okay, so solid collide is here. Now we are going to discuss this in a while, but I wanted to show you what is happening here. This falls and collide with the second box, which moves away, and then both of them, well, actually this is not reaching the floor, but this is, and you see that its centroid just gets stuck here, cannot fall lower than the floor. Okay, like this. Start to bounce because this is subject to gravity, this is not. Okay, so this will eventually stop moving when the effect of the collision just ends after a while. Okay, so collision in this case is just like a push applied on the corner of this box, just in one moment of time. So this action is not active, let's say, forever. It just collides with this box, and then this box is just simply free to move. So sooner or later it will stop moving. Okay, this depends on the iterations of this of the solver. If there is no force acting over an object constantly, then that object is basically destined to stop sooner or later, like this. This is stopping only because there is an equilibrium between gravity and the floor. Okay, else it will not be converged in this moment. It will be still falling down. Okay, so for example, if I unplug the floor from this object start to fall, and you see that the solver still say running, 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 and running. Okay, so it's different to reach an equilibrium because of the equilibrium between forces, and reaching the equilibrium because of an object that tends naturally to its equilibrium. But anyway, you see that the behavior of the solid collision is like this. Now, let me stop the simulation, Let me stop the simulation and reset it. Okay, so what's the important consideration here? Always, in this case, also there is basically no need to create other simulations. You can work basically with whatever solid. I'm using boxes because they are easier to create, but you can work with whatever shape. You see that rigid body asks for a part, and as a part, it accepts mesh or B-rep. It doesn't say box. Okay, so you can use whatever mesh you want or whatever B-rep you want, okay? Because the important thing in rigid body simulation are the planes. The fact that the rigid body is rigid is defined by this goal here. But the collision, for example, are based on planes, okay? So there is basically no need to work with boxes. You can work with whatever you want. One thing that I did here, okay, so let's discuss the solid collide. The solid collide asks for meshes. So the rigid body can work with both B-reps or meshes. The important thing is that they are closed, so they are solid, okay? While the solid collide only accepts meshes, and it says explicitly, like mesh A and mesh B. One thing that you might want to, let's say, take into account and be very careful. Don't switch, for example, rigid bodies and meshes or parts when involved into a collision or concentric or aligned phase. So for example, if this is, oh, and still you see that I am using here the centroid and the XY plane in case you want to change the collision, the reference plane of your rigid body. But in this case is not that relevant, but you might want to, for example, use the plane that comes from here instead of the XY plane that comes from here. They are absolutely identical, okay? So here you see there is mesh A and plane A. Don't switch them. If mesh A is this one that comes from this B-rep, then the plane A must be the plane that comes from the same B-rep or the same mesh, okay? So that's the only consideration that you might want to take into account. And one consideration when you start to work with collision, the strength. Now, I wouldn't change the strength in normal, let's say, in a normal balance between the strengths in Kangaroo. You see that here I'm not touching any strength, okay? So unless you do something weird, which is like, I don't know, tweaking the strength of some goals too much, then in that case you might want to tweak also the strength of the collision. But the strength of the collision is a force that basically tends to maintain one volume outside from the other volume, okay? So if you increase this strength too much, you might have some kind of unreal behavior, like for example, the collision effect being amplified too much, so it becomes unreal, okay? So I wouldn't tweak the strength of the solid collide unless you see some, let's say, behavior that doesn't correspond to the expected result, okay? And the other thing that I placed here is the grab, which is a particular goal, which is present here in the main group, is here. The grab is a component that allows to interact with the simulation in real time. So even when we run the simulation and it finds the equilibrium like this, okay, if I have the grab component plugged to our goals, I can still go here in the simulation and grab the object with the mouse, okay? So if I grab this object closer to our second box, there is the collision that basically avoid the two objects to overlap. So I can kick the second object away as I want because I can grab this and make it collide to the second one. You have to simply deal with the perspective here. Yeah, like this, okay? As the second one is not subject to gravity, you see that it's still floating around. Okay, so grab is something that allows you to interact with the simulation in real time while running the simulation, meaning while this is set to true. Even if the simulation is converged, the grab alters the equilibrium and simply switches back to running status. It's difficult here because I have gravity running, so I have to get closer to the plane, collision plane, and you see that I am missing it. Well, actually, because I was moving in the wrong direction. But anyway, you can reset it and play around again and again like this. Well, this was one hell of a collision, as you can see. So that would be the effect, for example, of having a high value for the strength of the collision. Okay. But anyway, this is quite funny to work with collision objects because they simply create rigid body interaction, which is the main reason why we create rigid body simulation. And I have some examples that we can discuss later on. And this is the other main collision that you might want to take into account, which is the solid plane collide. This is the last goal that we are going to analyze in terms of this toolbar. You see, we reached the solid plane collide. We still miss the beam and the support. Okay, but these are quite peculiar, so I prefer to discuss them separately from the other one and together. So what happens here? Oh yeah, sorry. Here I use this Heteroptera random direction because basically what it does, if I hit F5, I get a different orientation of my original box. Okay, but this is something that you can avoid. You basically can create an XYZ vector, plug it into here, and use, for example, 3 sliders between -1 and 1, 3 of them, in order to define a random or variable orientation of your box in space. Okay, so as you rotate this, you get a different orientation of your box. Now I was using this plugin here, Heteroptera, because it gives me a random direction for this direction here. But anyway, I will discuss this in a while. What happens here with this initial configuration of the system? But the simulation itself has a load applied to this box and has a collision with an horizontal plane. This horizontal plane, this collision plane, is set by default to world XY. Okay, so it's basically the ground floor that we were considering. Now, and of course, it has the rigid body definition, the usual rigid body definition. So when I run this, I have this behavior here, which is quite interesting because, as you can see, the main difference between the floor and the solid plane collision is that I can just recover the last simulation here, just switch between the two like this. Okay, here we have the ground, the floor, which is this goal here, which is not part of the 6 degree of freedom group. Okay, so what it does, it takes the particles of our system. Now, if we go back to our system definition, I'm going to turn off the preview and turn off the preview of the bouncy solver. If we go back to our system here, and we consider these boxes, the only particle, the only point of this whole system are the centroid of our boxes. Okay, so these are the only 2 points that the floor can interact with. That's why when we run this simulation here, we see that the object falls down, especially the first one, which is subject to gravity, falls down until it touches the floor, but its centroid is aligned with the floor, not the body. Okay, while if we work with a solid plane collision, it's the rigid body that interacts with the floor in this case. So it's not the centroid, it's the whole body. Okay, so that's the difference between the solid plane collide and the floor that is present into Gold's point, because these works with points while these work with rigid bodies. Okay, so this is very important to understand. Of course, if we want to work with a rigid body simulation, I always, and of course, I do recommend that you use the solid plane collide, like this one. Now, how does this work? It's very simple. It doesn't deserve any further exercise to understand. It takes the solid, okay? It asks for a solid, but in this case, for example, you see that it doesn't say BREP or mesh. Okay, there is no evidence, but you see that the black hexagonal icon is the hexagonal icon of a geometric primitive, which is basically the where is it? The mesh. Here it is. Okay, so pay attention to what type of data is asking for. So in this case, the solid is not a NURBS solid, it's a mesh solid. So I converted the original box into a mesh using the mesh BREP. Why I use the mesh BREP in this case and not a more careful conversion? Mesh BREP is not a careful conversion, so it's an automatic conversion. So it can create a complex set of quads and triangles during the mesh conversion. So it creates an irregular mesh. But in this case, it's irrelevant because I want this mesh to behave like a rigid object. So it doesn't matter what kind of topology we have for this mesh. Okay, so that's why you can simply use the mesh BREP configuration here. But you can use whatever. Well, let me play a little with this. We have here you can use whatever in terms of rigid body definition and solid plane collide, of course. Okay, but let me play around with this a little. So, for example, I'm going to work with some funny mesh right now. I don't know if you have these plugins installed, but it doesn't matter. You can work with whatever object. I have this plugin which is called Peacock, which is for parametric jewelry design, and it has also a display section with some body parts. Okay, and I'm going to take an ear, for example, which is this one. Okay, I don't care about the shape actually. I just need a mesh. Okay, so I'm taking this one here, this thing, and I'm going to move it like up. Well, it's already good because by default it moves up by 10. So I have time for this object to fall down. Okay, and then once I have this mesh, which is going to be my mesh, you see this is a very complex mesh. If I take the preview on and turn on the mesh edge visibility, which with Control M, you see how many triangles it has. Okay, so it doesn't matter the topology that we are going to use. The only thing that matters is that this is a closed mesh. Okay, and what I'm going to do, I'm going to plug temporarily this mesh into the rigid body definition and also into the solid plane collision. I don't know if the simulation was running, I guess, because you see that something is moving around right now. Yeah, it was running. So I'm going to try to find the solver. I think the solver was already saved inside a specific, a specific view. So I'm going to turn this off. Yeah, okay. So we can work properly. Reset everything. So I have this ear here hanging. And what I'm going to do, I need only to apply a vertical load to this here. So I'm going to calculate the volume, the mesh volume of this object. So it gives us the centroid of this thing. And I'm going to apply the load to the centroid. Okay, why? Because if I apply the load to the centroid, I am applying this load here to the whole rigid body. So it's different to apply, for example, this is a very complex mesh, right? I could also, for example, deconstruct the mesh like this, have access to the 3, 6, 6, 6, 5 vertices of the mesh, which are all these points here, and apply a load of minus 0.1 to these 40,000 vertices that I have here. But I then will have 0.1 multiplied by 40,000 global load applied to this object, okay? While as I'm working with rigid bodies, I can take advantage of the situation, take only the centroid or the barycenter of the object, and then apply one single load with the desired strength to that point. And this will affect the whole object, okay? So now I have the ear converted into a rigid body, and then I have the collision with the collision plane, which is the horizontal XY plane. I only need to define the solid plane. Now, the solid plane, I'm taking it from the planes of my rigid body. Okay, so I should see somewhere here. Let's see if I can find it. I should see a plane somewhere. Well, this is the plane. Oh, well, this plane is non-barycentric. This depends on how the mesh is, well, no, actually, this depends on this thing here. This is still using the barycenter of my original box, okay? So I need to provide the proper plane. If I don't provide the plane, it will use the barycentric plane. So here it is. This is the barycenter. Okay, so everything is set right now. I can basically reset the simulation and make this ear fall. Now, the problem is that this is a very high resolution mesh, so it will be slower. You see that it's very, let's say, discontinuous, like simulation. It's already reached the ground, and now it should start to fall, like on one side. I think this is going to be very, very slow. But if we see it, for example, from the right viewport and find the preview of our solver, like using this, let's see.
Yeah, sorry to interrupt that. Sorry, I have a doubt.
Yeah.
We didn't even use this floor, right? Floor component. So how is actually it's stopping in a zero plane?
Let me stop the simulation from running, but in the meanwhile, you see that this here is starting to fall on one side, okay? So the horizontal plane, which is the collision plane, is defined inside the solid plane collide. And this solid plane collide has a collision plane, which by default is set to world XY. Okay, but you can change it. Okay, so later on I will show you. Well, later on it means in the second class, in the second session. I think we will take another 10 minutes because we started with some delay. But in the second class we will be playing around with this collision plane to see some examples. Okay, but this is where you define the collision plane. Okay, so here if I make this simulation run a little more, you will notice that this here, step by step, is basically falling on one side. And this is a rigid body. When this part here will reach the ground, this object will start to, let's say, balance around. Okay, so that's the effect of this rigid body. You can work with whatever body you want. Okay. And the rigid body is absolutely more effective than the floor. In this case, in this particular case, with 40,000 vertices, you might also work with the floor, because we have 40,000 points all around this body here. So it will be basically the boundary representation, meaning the external surface that won't be able to pass through the floor, and not the barycenter. But I still recommend that you use the solid plane collide when you work with rigid bodies, because it's more effective. Okay, so you see that this thing is falling down, it cannot pass through the floor, and it's taking the proper orientation in order to lie on the floor. And you see that is starting to balance around. Here, this part is going, it's going to raise up. Momentarily, it can also fall down with respect to the floor, but then the solid plane collide will rise it up in order to lie on the floor. And you see that we already came to quite an equilibrium phase. And this is very nice because you can use this in order to simulate, for example, the natural distribution of object over a surface or over a plane in this case, while falling randomly. So you can also program some kind of I don't know if you saw sometimes this kind of animations where you have like for example walls tumbling down or collapsing or something like that. Okay, so you can use this kind of simulation for creating this kind of effect instead of a human here. So I will eventually reconnect things properly. So I'm going to stop the simulation here, and also let's get rid of this human ear, and let's go back to work with this mesh here, and also with this mesh here. and also with this, well, actually the point was the centroid, the application point for our load. So let's get rid of the human here. And if we go back, we should see, yeah, here we have our original box. We must reset, and this will fall down. Yeah, okay. So there it is. We are back to normal. So these are basically the main components. Well, I will leave it this definition with the original components from standard Grasshopper installation, but I do recommend that you take a look at the webinar that is happening in 1 week from now, basically, where we will discuss Heteroptera. Okay, so Heteroptera is one plugin that I value the most. It's very, very important in any of my workflows. So take a look at it and start playing with it. And if you want, just watch the webinar next week. So this is basically all our solid. Sorry, let's switch back also to Kangaroo 2. All these 6 degrees of freedom, but the beam and support. We still miss these two things here. Okay. So chat. Let me see what happens in the chat window. Yeah, the beam, exactly. The beam is exactly what I was saying. The beam is the more complex one. Okay, the beam together with the support are the two most complex. Well, the support is not complex, but as it works with the beam, and I want to show it together with the beam, I left it like the last component. Now we don't have time today to discuss this, okay, because it requires quite a bunch of time and lots of consideration. But this is what we are going to do as the first thing in the second session of this course. And we will discuss this in detail, because this is something that, for example, if you are an architect or you are somehow into construction industry, then you might want to take a look at this very carefully. So we will discuss it as the first thing next Thursday. So basically here I prepared some kind of small examples. Okay, so you see that it also introduces, for example, the support, because it's quite simple to work with, and I prefer to, let's say, give you a glimpse of this kind of behaviors in a more complex configuration. So here we have 3 boxes. Okay, these two boxes here are just floating. This one is anchored to the ground, like along this line here, this edge. A vertical load will push this box up. So as it is anchored here, it will rotate along this axis, will collide with this box. This box will be, let's say, sent horizontally towards this plane. This is a collision plane. This box will bounce on this plane and will collide on the second box here. Okay? So it's like a chain of collisions. So if I run the simulation, this is what happens. Chat once again. Let me see. Sorry, let me see. Can we get recorded video? This session is already, I think it's already recorded. Let me double check. It should be recorded. Yeah, it's being recorded. Yeah, okay, perfect. Yeah, I was panicking, but anyway, yeah, it's being recorded, so you will have it available online today, just today. So you see that this is what happens. You have this chain of collisions happening. Now, the only important thing here is this. Now, if you take a look in particular at what happens in this part of our box, okay, you see that this box is basically initially is lying on the floor, okay? And if we take a look at this from, for example, the front viewport, I'm going to place a little point. I don't know if you can see this point. It's very small. Well, actually, let me create a small circle here so it's more evident, okay? So take a look at this circle. Its position with respect to this edge. It lies at half the height of the box, of course. If I run the simulation, you see that this box is rotating along this point here. Okay, so I'm not using anchor points in this moment, because if we consider the box has no point in this place here and along this axis. Eventually, its vertices are here at the corner of the faces. Okay, so what I was using here is exactly a support. Support is the way you create physical support. As we are dealing with 6 degrees of freedom, the support is the kind of constraint that allows to specify what type of constraint you want to create. So you have the standard X, Y, and Z movement or displacement, and then you have XX, YY, and ZZ, which are the rotations. Okay, so you can basically restrain one object from moving around by specifying what type of constraint you want to create using this support. And take a look at how it works. I created a first box, which is this one, exploded this box, and had access to its faces. And then I selected this face here. I evaluated this surface in the center point, which is, by the way, point 0.5, 0.5, as we did before in a previous example, and reparameterize the surface, of course. So we get this frame. Now this frame is aligned with the face. So its orientation is the same orientation as the face it belongs to, and its origin is the center point of the face because we use the 0.5, 0.5 into a reparameterized space, okay? So this frame, I'm using it as the plane for the rigid body definition. So my rigid body has a plane which is not barycentric. Originally, it would be this one. But I don't want to use this plane during the rigid body simulation. I want to use this one. Remember that it's a common mistake to think that the plane of the rigid body somehow affects the collision. No, it doesn't affect the collision. It is a plane that you can use during the simulation to affect additional goals. Like, for example, the support goal. So I want the support to be placed with correspondence to this plane here. Okay, so if we take a look, if we turn off the preview of evaluate surface and take a look at the rigid body preview, you see that the plane that corresponds to the rigid body is exactly this plane here. Now, what does it mean? It means that what I'm doing here, I'm using as the support placed along this plane. Now, actually, this is not properly correct. This is the easiest way for me to define the object plane. But when you think, for example, in the real world of vertical translation, for example, vertical displacement, vertical means along the vertical z-axis. While if I use the evaluate surface, the frame is aligned with the surface. So the z orientation is the normal to the surface. And therefore, the z-axis is horizontal. This is important because when we say that this support is avoiding the z displacement, and is set to true, is not avoiding z displacement along the vertical z-axis, but it's avoiding the displacement along this z-axis, so it's horizontal. So the proper way of defining this frame here should be to create an horizontal frame corresponding to the center of this face. So I should take eventually an XY plane, take its origin corresponding to the point of the evaluate surface like this, and use this as the plane. So now, when I say Z movement, it's not possible because this toggle is set to true, it means that this body, this part of the body cannot move vertically. The rest of the body, yes, but this part, no. So everything is back to normal. But in this case, for example, if I want this object to rotate like it was rotating before this change here, I cannot leave the X rotation free, because if I do this object will rotate along the longitudinal axis. While I want to leave the rotation along the Y axis free. So I set this to true because I want to avoid the XX rotation, and I set this to false because I want to allow the YY rotation. Okay, so that's the way the rigid body plane work. According also to the use of the support, which is one of the more important constraints that you might want to use in your simulation. So if I reset and run this, you see that we have exactly the same behavior. Okay. Now, of course, you see that there is no collision happening. Why? Because our plane was also affecting the frame, was also affecting the plane A for the solid collide. But now I don't want to work with this. Okay. I want to work with the actual body plane. So if I repeat this, now I have the collision back up and running. Okay. So this is a proper consideration for the object rigid body plane, the meaning of the rigid body plane, and the way you set up the body plane properly. Okay, so that's why I wanted to show this not only for the support, which is basically it's pretty straightforward. Okay, but for the correct rigid body plane definition. Okay, now we will eventually take a look at these other example here in the next session. There is also there is a couple of examples here. This green thing is for let's say inflatable structures. Okay, so eventually, as discussed, we will deal with this as the last topic if we have time.